house material into five. Okay, so there are a lot of breaks in between. So don't worry. It's a 5 hours training. I'm here. Have a coffee here. So I should be fine. So I do this a lot. So don't worry. Don't let the terminologies, the big names, scare you. Okay, that's why I'm here. I'm going to kind of simplify it. For those of you that have studied electrical or whatever, you probably are familiar with most of the concepts here, even those with physics. But I'm probably going to be coming to teach you from a different angle, not from a theoretical perspective. Uh, yeah, I do a lot of reading and stuff like that, but no, not from the theoretical perspective. I'm going to be explaining things from you from a different perspective. So let's go inside. Let's get started right away. Okay, what is wavelength? Uh, What is wavelength? Okay, that's a question that we ask ourselves. What is wavelength? We hear it a lot. We discuss it a lot. We say that a lot. We try as much as possible to say, hey, wavelength is this, frequency is this, amplitude is this is this. But look at the picture there. Look at the video. Okay, look at what I have there. That is what I'm going to be using to explain the concept of wavelength, frequency, amplitude, and phase. It's a very simple terminology, and this is the basics of radio frequency, RF. This is the basics of any field you find yourself because we are talking about the frequency and the wave. And the wave cannot be without the frequency. And the frequency cannot go without a wavelength. So what is the wavelength? It's the distance. Okay? The distance. What distance? Okay, let's go into it one by one. Okay, let's kind of understand what is distance. So you see the word wave and length. Wave and length. So we're talking about a gap. Okay, we're talking about something, a dimension. So the distance over which the wave shape, okay, repeats itself. If you notice in the previous slide, it is just repeating itself. It's kind of the same thing. It's boring, right? Showing the same pattern and it's going up and down, up and down, up and down, showing the same pattern. It's kind of boring. But if you look at it very well, the distance, okay, when if you look at the shape, it's the same pattern. That's the distance. The higher finger is an alternating current. So you can see it goes up and down. That's it's kind of continuously oscillates between positive and negative. So each oscillation, or you can call it a cycle, okay, involves a complete transition from the positive to the negative. And guess what? It comes back again. So it's a back and forth thing. So if you look at it from that perspective, then we can say that the wavelength of an RF is the distance between, can you see? The distance from here to, you can see my mouse, right? So the distance between two successive peaks. Um, in radio frequency terminology, we call the peak crest, okay? Or two successive curves, or the valley. Can see the valley. Okay, so that is what we call wavelength. In a simple term, let me just put it in a simple way. The wavelength is a distance that a single circle of an RF signal covers as it moves through the space. So in RF engineering, it's critical, very important for you to understand the inverse relationship between the wavelength and frequency. Okay, it's critical to understand the relationship between what the wavelength and the frequency. Now, the relationship is described in a very interesting way. It's in three things. Now, if you notice, I've been talking about two things so far. One is the frequency, and it is measured in the hertz. The second one is the wavelength, is measured in meters. But there is this third property that I did not say anything so far about. It's the speed of light. What has light got to do with what we're talking about? You know, radio frequency is part of the spectrum of light. Yeah. The challenge with it is that we cannot see it. Why did you say that is light? We can see light. Come on, buddy. What is this man saying? I didn't say it is light. Yeah, we can always see light, but there's a spectrum of light that we can't see, and that is the part that is under the radio frequency. So it is a third property of radio frequency. So you're going to be using that. And the speed of light, do do you remember what the speed of light is? Who can remind me? Okay, I'll help you. So the speed of light is 300 million meters per second. That's okay. That's okay. So I try not to put in a lot of numbers because I don't want to scare anybody. Okay, I don't want you to feel uncomfortable at any time. But so far so good. Uh, so far so good. Are we okay with what we've done so far? Thumbs up. So at the bottom right, you will see a reaction thing. So you can give it thumbs up or thumbs down. Okay. Thumbs up if you understand, thumbs down if you don't understand, okay? So I can quickly report to myself. Awesome. Good. Awesome. Okay. So let's go for it. So the second property is the frequency. That's what I've mentioned earlier, right? So as I mentioned earlier, so an RF operates as an alternating current that cycles in the form of electromagnetic waves. So remember, see, we can see, right? That's electromagnetic wave. That is the part that you can see. But there's some other waves that you cannot see. And that's the difference between us and maybe dog or cat or whatever. They can see beyond what we can see. But anyway, so this is a spectrum. And the radio frequency is also part of it under the electromagnetic waves. I'm very sure most of you are familiar with that. So I'm not going to spend much time here. But what I want to mention is that the categories of frequency under the way radio frequency range. So we can categorize it as high frequency or low frequency or thereabouts. And as I mentioned earlier, frequency is measured in hertz, so we can see it from that perspective, like your access points, your phone operates on some of them operates on 5 gig or 2.4 gigahertz. Your Zigbee, your Z-Wave radios, your Sigfox, there's some 1 gig. You find them like the IoT radios, you find it like around 900 meg and stuff like that. Okay, so let's get things a little bit more interesting. It's okay. Don't. This is still all physics that you did when we were in secondary school, so I don't know about the panic yet. So how do you figure out wavelength and frequency? The relationship is very straight. It's just c, that's the speed of light, equals to the wavelength, that's frequency. And yeah, we can easily get this from different angles. So when they give you a frequency of like a 2.4 gigahertz that you find on Wi-Fi, If you put that into your calculation, then you realize that your uh, wavelength is actually 0.125 meters. That's 12.5 centimeters, right? So that's pretty cool. Your 5 gigahertz, it's just 6 centimeters in the wavelength, right? So that's pretty cool. I want you to visualize what I'm saying because radio frequency is kind of abstract. You can see it, but I want you to visualize it. That's why I'm putting this into the context, right? So your 2.4 is 12.5 centimeters. The 5 gigahertz is 6 centimeters. Pick any frequency that you have been familiar with or you have heard. Just put it into your radio station, right? Uh, whatever radio station that you listen to, BTS or whatever, take that frequency and kind of put it into this formula and then have an idea of how long your wavelength is. Okay? So, we're talking about wavelengths, we're talking about different perspectives. There's what I call amplitudes. Okay? Amplitudes is pretty much uh, the heights. Okay? It's the heights, kind of. So, it's very easy for us to understand the amplitudes from that perspective. Because it represents the strength, it represents the power, and we use it a lot in making decisions in RF. Okay, so amplitude can be defined as the maximum displacement. So let's assume that there's a flat line. The maximum displacement, okay, so it goes up. Sometimes I know you probably must have heard it before, that wave is a disturbance, right? So you have like a flat signal. So when you put in the power, it jumps up like you throw a stone into the water. It jumps up, right? Okay. The maximum displacement of a continuous wave, okay, from its natural or baseline position, okay, that is what we call the amplitude. Okay. Um, I can illustrate that. Can you see my screen? So this is spectrum analyzer. Okay. So this is how you see signals in spectrum. Can you see? So this is the amplitude, right? At the top here. Can you see? Can you all see? So the amplitude for
Yes,
this
sir.
particular signal. If you look at this other signal here, this is another amplitude, right? Yeah. So we can look at it from different perspectives. Let's look at 2.4 gigahertz. This is more beautiful. You can see the way the signal goes up, right? So you can see from the way the signal goes. So this is how we look at frequency from different perspectives, right? This is you can see from the time uh, or frequency perspective. So you can look at it from here or from here. So if you look at the 6 gigahertz as well, you see 6 gigahertz, and then the bandwidth. See the bandwidth here. You can see the bandwidth here as well. There's a signal from here to here. And here you can see from here to here. We're going to be doing a lot more, and sound and stuff like that. I'm going to give you opportunity for you to play with spectrum analyzer and stuff like that, so you can familiarize yourself more with stuff like this. Okay, so let's continue. Okay, so back. Everybody start. Okay, pay attention. Okay. All right. So we've not gone far. So let's go to what is phase. So when we refer to phase, phase is another important characteristic, like I mentioned earlier. So it's a characteristic of wave. It specifies the location or timing of a point within the wave cycle. Now, it's a repetitive waveform. Typically, it is in the phase difference that we usually pay attention to. Not actually the phase itself, it's the phase difference. So if you look at it, there's a signal going up, and then if you look at the top here and the top of the second signal, that is the phase difference. Okay, so that is what we pay attention to the most. Okay, because excuse me, when two waves, for example, are added, the difference between the phase of the two shapes is important in determining the resulting waveform. Because that is what makes the new waveform. So the phase difference between two waves of the same, not what I said, of the same frequency moving past a fixed location, okay, is given by the time difference between the same position within two waves or two sounds. So you look at the peak, okay, or the positive one, okay, that is what you use in making a decision to identify what is the phase difference. You may be wondering, like, what's this guy saying? Okay, see, the two waves of the same frequency that are perfectly aligned, they have what we call zero phase difference because we say they're in phase. That is, they're together, they're in phase. However, when two waves that are in phase act to produce wave together, the amplitude equals to the sum of the amplitude of the two waves. You're not getting it. So when we have wave A and wave B, but wave A and wave B they look alike. So we can call the two of them as wave A and wave A. Just that just they look alike. If you combine them together because they're together, they're in phase, it increases, it amplifies, it increases. That's what amplify. It increases the amplitude. See, if one of the two waves, okay, of the same frequency is kind of shifted by one half, like I have up there, right? By one half, okay? It's shifted such that one wave is at maximum, the other one is at minimum, like here. One is up and the other one is low at the same time. Okay, they will call it out of phase. That is, it is out of phase totally. So these two are out of phase, and then what happens is that when they're out of phase, they cancel each other. Pap, they cancel each other. It's just cancelled out. So this, guess what, is that principle of what we call noise cancelling. You probably have an earphone or whatever that you use that has a noise cancelling. Instead, those that do sound like all these sound engineers and the likes, you have an earphone on that cancels the noise and stuff like that. That is a concept that is used for noise cancelling because what they do is to ensure that the frequency that is coming in is identified, and then they duplicate the same frequency, but then make it out of phase. It cancels it out, and then you have your noise cleared out, and you can clearly hear your sounds. You understand? So let's quickly talk about the next concept with propagation. I need to double up. I'm running behind time. Okay, so okay, I've changed to this box. Um, yeah. aware of the concept of the reflection, refraction, diffraction, and scattering. These concepts are the types of wave propagation behavior. So absorption, yeah, is one of the most common RF way of losing signal in RF. Excuse me. When an RF signal encounters a material, a portion of it is absorbed. It's the wall, it's your laptop, it's even your body is absorbed. And that is what reduces the signal strength. You know, we have a lot of concrete walls, we have a lot of metal walls, your windows, everything that's burglary proof, your gate, all sorts, almost everything that the signal touches, it kind of dampens right away. You see, in 2.4 gigahertz, the, passing through a concrete wall will make the signal strength to lose about 75% of the strength. It goes. And that is why in mobility, your phone, the signal because of the wavelengths, you use the frequency of the signal that comes from mobility can still penetrate through your walls, but your Zigbee, your Wi-Fi may not be able to achieve the same penetrating power because of the frequency. They are a little bit higher, like 2.4 and stuff like that. Whereas if you have like your your Z wave, it can kind of go a little bit, you know, and stuff like that. Reflection. You do that a lot. Every time you go to the washroom or you're in your bedroom or you're in your room or you stand in front of a mirror and look at yourself. Or you can take a touchlight and flash it to the glass, to the mirror. It kind of send the signal back. Same thing happens with Wi-Fi or in RF or in mobility or in IoT. The signal gets reflected back. It's just boom, boom. And that sending back concept, it's what results in what we call multipath. It's a phenomenon. The phenomenon called multipaths. You see, I was going to talk a lot about what multipath is. Multipaths phenomenon is when the signal is the same signal. You start seeing it bouncing around from different directions. This is as a result of reflection. Another concept is scattering. Oh, scattering is a very bad, it has a very negative impact on RF. Things like scatter signals, the dust, your trees, uh, buildings, the rough surfaces. Sometimes we paint the wall and then we make some rough surfaces on it. You see that a lot. Some they say it's design, some they say it is for security reasons and stuff like that. The concrete that they put that rough surface kind of affects RF propagation, but people just like it because it looks cool. Refraction. This is a concept that I want you to pay more attention to because it's the bending of the radio frequency. Can you see? The signal is bending to another direction. Now, it's bending is bending of the radio wave as the signal pass through the medium with different density. That's the key. Density. Problems of seen look up after rain, a rainy day, and then you look up and see uh, rainbow. Okay, it's as a result of light passing through the dense air at that particular time. You can mimic it. You can try to put oil or something on the floor and point your light at it. It will reflect and refract it. You can see different colors, separations. So, but it's the density that makes the difference. You can flash your light through any material and it will not disperse. It will not separate the colors. because the density is not that deep. But when the density is there, it's explicit and you can see more. Yeah. So the same thing with diffraction. It's also the bending and the spreading, but this time around is around the material, like a stone and stuff like that. Attenuation. So when we hear the word attenuation, it means loss. Okay. So uh, when you have a signal, the reduction in the signal strength or the amplitude. Remember, I told you earlier that the strength is the amplitude, right? So how we mixing the two words together, I will call it signal strength or amplitude, whatever. So I mean the same thing. Okay. So this reduction in strength can happen whether the signal itself is going on its own, maybe through the cable or through an open air. You wonder, like, what do I mean by open air? Yes, reduction happens in open air. See, let's start with wired. In the wired portion of the communication, where you have your RF cables and stuff like that, the alternating signal can actually lose strength due to what we call electrical impedance. I know most of you that did probably electrical and stuff like that, you understand what I mean by impedance. Impedance is the same thing as resistance, but this time around you have your capacitor or your inductor, not resistor this time around, but it's the same concept. So for those of you that are not familiar with that uh, idea of impedance, but just see impedance as, say, resistance. Okay, so it's like due to the impedance is the measure of resistance within the cable. Okay, so you have like the cable, you have like connectors, your different kind of adapters and stuff like that. But in open air, okay, in open air, the spreads, okay, the spreads as the air, as the signal is spreading through the air, so many things affect it. The absorption, like I explained earlier, the distance as it's going, sometimes even multi-part effects. There's one called relation theory. Okay, I will go into that. Okay, so the multi-part effects when the signal reflects from different objects. So it's this one object A. It's the same signal. It goes so now one is lagging behind the other one. One is so the concept of multi-parts. Now let's connect this back to where I was coming from about signal being amplified and signal being cancelled, right? So multi-part can actually result in any of those. Can make it stronger, it can make it weaker. It depends. So let's look at it from this perspective. A 2.4 signal, a 2.4 gigahertz signal passing through a wall or will attenuate around 12 dB and losing almost everything. If that 2.4 signal is passing through a drywall is what we use mostly in North America. We don't use concrete, we use wood for our walls. So it's drywall. Drywall will give you a 3 dB instead of 12 dB that we experience in concrete. So drywall will kind of dampen the signal by half, but in concrete will reduce it by 1 over 16. Can you see the difference? So the material that which is eating matters. So it's a very strong, thick material. It gets absorbed very fast. And if it is something that is not so thick, it gets absorbed, but it can still pass through. And the whole concept of spreads and the signal is going over a distance is being analyzed more under one called free space path loss. What I'm saying is that even in the free space, without physical obstruction, without any wall or concrete, RF signal naturally loses strength over distance. Okay, so and the concept is all called free space path loss. So FSPL, let me call it in short. FSPL occurs because as the signal moves away from the antenna that is transmitting it, it spreads out over a large area. It keeps on spreading because you cannot, it's unbounded. So it keeps spreading. And as it's spreading, its intensity is weakening. Let me bring you to something that you are probably very familiar with. I'll use the lights, you know. So if you have a touchlight and you turn it on, as the light is coming out, after a period of time, after a distance, the impact of the light is not seen anymore because it's only your close range that you can see the impact of the light. So the same way, that is exactly the same way signal Wi-Fi radio frequency or any signal that is under the electromagnetic spectrum behave. So as you go out from the antenna, from the transmitter to the touchlight, is the transmitter, right? As it's coming out, it spreads out and it attenuates and dampens. Okay, power measurements. We're going to talk about noise generally and signal strength. And let's understand that. And we're going to be talking about voltage standing wave ratio, how it impacts um, radio frequency. So let's get started. Um, okay, so the unit of power and comparison. So that's what we're going to be talking about right now. Okay, so when designing radio frequency network generally, there are two main goals that come into play. One is coverage, and the other is performance. You can imagine if you bring out your phone or you bring out a mobile device or anything, your tablet or whatever device that you're using, and you check it, and all you say, "Oh, no network. Yeah, it's bad, right?" Or you bring it out and it's saying loading, loading, loading. That is bad. Okay, you ask yourself the question, who is the engineer that designed it? That is bad. That is your work. So you need to have that at the back of your mind when you're designing, when you're constructing, when you're doing all sorts, whatever, regarding to your deployments. The two things that comes to mind is the coverage and performance. Achieving these goals requires a solid understanding of radio frequency power management. And that is why I want us to spend a lot of time here, okay, to understand the units of comparison, understand the basic RF mathematics. Believe me sincerely, knowing the units of power and comparison will actually help you a lot to understand what radio frequency is all about and how they interrelate is the key in making an informed design choice. Okay, so let's go into what we want to talk about today. The one called the absolute units of power. Yeah, I know most of you are familiar with it, okay, but I will try as much as possible to explain it in a different way. Okay, so look at it from this perspective. When I say absolute units of power, it represents a known value. You know that value. That is absolute. That is what I mean by absolute. You know the value. You're just comparing it. You know that value. There's a direct relationship. Let's say like 12 Congos of Gary, you know, it is a measurable quantity because you know the units that you're using to measure it. It's the Congo, right? I don't know what they call it now, but those days they call it Congo. What do they call it now? Who can help me? You know what I mean? Uh,
Yes, sir. It's still Congo, sir.
okay, great. Yeah, yeah. So that's it is measurable. When it is measurable, that is when you call it absolute. So look at it from this perspective. So these units that we use to measure, transmit, and receive power in RF signal is what we're talking about here. And most common absolute units that we use are watts, milliwatts, or decibels. Decibels relates to 1 milliwatts. Okay, so you use dBm. You'll be seeing a lot of conversation henceforth in dBs. In radio frequency, we often use dBs than wattage. Wattage and milliwatt and stuff like that. You see that a lot more in high power. Most of you in electrical world, that's what I mean by that. You see that often in high power and not in low power. Okay, so let's talk about the second concept, which is called the relative units of comparison. Now, this is a little bit funny, but you get it, the concept now. Okay, so relative units are comparison-based measurements. So what it does is that it indicates how much power has gained or lost as it moves from one point to another. Okay, look at it. Think of it as you're comparing one signal to another rather than measuring the absolute value. You're not measuring it, you're comparing it. So you have a benchmark that you're using to compare. Okay. Okay, for instance, if you have a signal, an RF signal that travels through a cable, okay, like this cable, that travels through a cable, okay, and then of course it will experience some loss. Then we can use relative units to describe the reduction in signal. Let me take you to what I'm trying to explain. So relative units are helpful in comparing transmitters and antenna types. I will explain to you in a very easy way. Okay, so we use decibel, we use decibel in relation to isotopic radiator. I'll talk about all those terminologies later. We use decibel as related to half wave dipole. Please, if I'm saying something that you don't understand, just call me back. Don't forget that, okay? Always call me back. You don't need to wait for me. And feel free to interject at any point. Okay. Earlier I was talking about the absolute value when I said you can measure it, right? But when you're comparing, you have a benchmark that you're comparing something to. So you're like you're using um uh, uh, let's say uh, uh, 2 times of Margaret's height. Oh, Israel is 1.5 taller than Margaret. So my comparison is Margaret, right? I could say that, oh, yeah, Boluwatife is the same height as uh, Toby. Do you get that comparison? Do you understand what I'm trying to say? Right? So instead of calculating and trying to understand the whole maths behind a particular transmission, you use the known value and compare what you're trying to detect the new one with the known value. So the old one is a benchmark while you're using the new one to compare to it. Does that make sense? I need a thumbs up or a thumbs down. Okay, great. Okay, great, great. We're good. Go for it. Yeah, what's the question?
Yeah, what's the question? No, no, it's a mistake.
Ah, okay. Great. Okay, so let's go. So I talked about the watts earlier. So what is watts? What do you say watts? You guys all are familiar with what, but I'll still explain it just for the benefit of doubt. So, of course, it's the fundamental unit of power. It's named after one dude named James Watt, and the Scottish guy. But let's just talk about the main thing. 1 watt represents the power produced when an electric current of 1 ampere, okay, 1 ampere flows at a volt of 1 volt. Ah, just don't bother yourself with all those terminologies, okay? Let me just explain the concept of watts. So I like to use analogies because that sticks better than all those big English and stuff like that. And I've been in a car wash before, and see the guy carrying hose and spraying the car. I mean, you're familiar with that concept, right? So the power washer that the guy is holding the hose connects to the water source, right? Okay, and then uses high pressure to clean the surface of the car. He presses something on the hose that will force the water to like a jets. It comes out, boom, and wash the car. Okay, so there are two concepts there. There is a water pressure, that is a force that is applied to the water, and the second is the water flow. Okay, the water flow, that is the volume of water over time as water is flowing. Okay, so these components together determines the power. Okay, it determines the power of the water stream. That is what we're talking about voltage. So increasing either the pressure or the flow. So it's either it increases the tap to increase the flow, or it uses that force, that jet controller in his hand to increase the pressure. Okay, either way increases the power of the stream that is cleaning the car. So similarly, that is exactly the same concept in electricity, anything electricity, right? Either it's radio frequency or whatever, the same concept. So the voltage takes the place of the pressure this time around, and the current in amperes takes the place of the water flow. So it's flowing, that's the current, and the pressure is the voltage. Do you get the concept now? So you can say that power, the wattage, equals to volume or the voltage times current, or like the pressure times water flow. Do you get the concept of wattage now? Thumbs up. Okay. So that is voltage. Milliwatts is just a smaller version of voltage. It's the same thing. So watt is watts. Milliwatts is just like saying 1,000. That one wattage you have divided by 1,000. Okay. The reason why I need to introduce the concept of milliwatt is that unlike high power, we really don't deal with wattage that much. the the signals that we have, the power in it, they are usually very low, like milliwatts. That is why you can carry your phone with you and you don't get shocked. You don't get all this whatever easily because the power in it, it's pretty much very minute. It's a very small power. You don't have a lot of power in it. Okay, so that's the difference, and I just need to kind of amplify that all these access points or transmitters, they're being operated with milliwatts. We don't use wattage. You see wattage a lot in electrical transmission, like a generator and stuff like that. But anyway, that's just what I wanted to talk about in terms of voltage and milliwatts. And of course, there are different types of uh, power measurements. So many vendors specify the transmit power in form of intentional radiator. I will explain what intentional radiator to you guys soon. So it's kind of represents the signal power before the antenna gain, and then some other folks they kind of represent uh, power in form of EIRP, that is equivalent isotopically radiated power, which is like more or less a factor in the antenna gain. So it provides the effective power output as radiated by the antenna. So one is before the antenna, one is together with the antenna. That's just the difference, pretty much. But I'll explain what that means later. I just want to build the foundation for you, okay? So you're going to be connecting the dots together. From so the interesting guy that I want you guys to pay attention to a lot more. Okay, this is an interesting guy. It's So if you don't know anything from what I'm going to be teaching you today, please understand decibel. It's super important. It's Without it, everything we've done today is a waste. So please, let's come together and pay attention. Okay? If you are munching or eating something, this is the time to quickly drink water and kind of listen and pay attention. Okay? So decibel is unit used to measure the difference in power between two values. So I mentioned earlier that there's one called relative measurement and absolute measurement. Remember? So it's we use it for relative measurement a lot. So in radio frequency generally, either you're dealing with mobility or you're dealing with Wi-Fi or you're dealing with IoT. In wireless network in generally, decibels are commonly used to compare the output power. Okay, so we use to compare the output power of the transmitter to the received power at the receiver. So you know what I mean by transmit power? The transmit and the receiver, right? So there's one side and the other side. So why do you do wireless anyway? We we usually do have transmission done over wire. So from one end to the other end. We were trying to eliminate the use of wire for so much, right? So we're trying to remove as much as wire that you can remove. So that particular distance that is not wired is called wireless. So you have point A to point B. So there's a transmitter and the receiver, and then everything continues again. Then the wire continues. So, but in between is the gap. That gap is the wireless network. You get it? Okay. So that is what when we talk about the output power, the transmitter, and then the receive power and the receiver end. Decibels are especially useful when assessing signal strength, either it is lost or gained due to obstacles like trees or distances, space patterns, right? Or the way you have your antennas configured. So those things are the things that can actually affect the signal. You can make it better or bad. Remember that. Okay. So I won't talk about the origin of decibels, about the history of decibels, but uh, just for you to know, decibel is derived from the word bell. It's a unit created by an engineer called Bell Telephone Laboratories to measure power loss over telephone lines. So it's a very ancient word, but I want you to just pay attention to it. Okay, let's go about decibels in wireless. So decibels simplify wireless measurement by allowing us to kind of express significant changes in power in a more manageable way, not using watts and stuff like that. That is going to look a little bit complex. So we like to use logarithms in wireless calculations rather than using um, normal calculations, see 1000 and stuff like that. Today, you're like, oh wow, these numbers are scary. But when you use logarithms, it looks a little bit simpler and easy to understand and comprehend. So you don't want to say that wireless engineers are lazy. We are not lazy. We just like to represent things in a very simple way, not to scare people away. Okay. Okay. So this is the formula. So dB is 10 times P1 over P2 log 10. So P1 and P2 are the two power levels. So like I explained earlier, you could take it as you want to see something, Israel?
Yes, sir.
Okay. It's like you're comparing your output power versus the receive power. So these are the two things, and then you calculate it, and that's how you do decimal calculation. So well, we use decimal in measuring antenna measurements. We can like use it to express the gain. So depending on the type of antennas, like we can say in relative to isotropic radiator, that is, use it to compare an antenna gain to theoretical isotropic antenna. That is, it radiates, when you say isotropic, it radiates in all direction. An example of an isotropic antenna or transmitter is the sun, SUN, sun. Oh, okay. So you cannot achieve a theoretical isotopic antenna. You cannot. But we use it as a benchmark for measurements. So the sun radiates in all directions. So think of it like a spear that radiates in all directions around it. That is an isotropic radiator. So we compare antennas in dBi just to see um how we can just in that relationship for relative measurements. So a higher dBi value indicates that it's more focused antenna, and then we also use what we call dipole antennas. Dipole antennas, they're like half wave dipole antennas. So these are more common. We see things done in dBd a lot more. Uh, let's to uh, I have a material for you guys here. Uh, Just to some interesting calculations to understand and say I would da, 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 da. Okay. Da, 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 da. Okay. We almost done. So let's do this calculation. So this is how we do. Where's my controller? Uh, share, share, that's fine. Okay. This is how we do calculations when we are doing some maths in terms of dB. I will walk you through it later. I just want to give you a heads up how we do this decibel calculation. So what we do is we use dB like in threes and twos. When you see 10 dB, we multiply it by 10 or divide it by 10. Depending, if you're increasing it by 10 dB, then multiply it by 10 in watts. If you're reducing or subtracting by 10 dB, then divide in wattage by 10. Let me give you an example. Don't worry, I'm going to share it with you. Don't worry. Don't worry, I'm going to share it with you. So let's say uh, we have voltage, okay? So how do we do the calculations? Let me find an easy one. We have 2 dB. I think it's best I walk you through the calculation one by one. Okay, let's do this first. Let's do this one first. Okay, let's do this first. Okay, so what is 10 dB? Okay, so 10 dB equals 10 watts. Okay, what is 3 dB? 3 dB means 2 watts. So if I have 13 dB, it means 10 plus 3, right? Are you with me? I can see you. Uh, can you see my screen? Right? Good. Okay. So when you see good, that's fine. So when you see 13 dB, 13 dB equals 10 plus 3, right? That is 10 times 2, and that is 20 watts. Do you understand? Okay, let me give you an example. If you have 36 dB, what does 36 mean? 36 is 3 tens and 2 threes, right? So it is 10 times 10 plus 10 plus 10, that is 3 tens, right? So if you go to the wattage side, that is 10 times 10 times 10, that is 10. That is 1,000. Okay? Hold on to that. Uh, uh, so that is 1,000. And then you have 6, that is 3 plus 3. That is 2 times 2, that is 4. That is 4,000 milliwatts. And that is 4 watts. Do you understand? Let's do the calculation together. Oh, you got it. Oh, great. Okay, great. Okay, I was scared. Thank you, thank you, thank you. But I will still do one more example, just in case. Okay, I just let's look at 27 dBm. Okay, 27 dBm will be you have two tenths in it, right? Two tenths. Okay, it's a little bit tricky. You can't do 10 in
Why?
27. Instead of using 10 in 27, Israel, can you please go and
Well, I
mute?
mean,
Okay, sorry. So 27 is a little bit tricky because we can't use tens. If you use tens, then there's a 7. 7 is not, you cannot, there's no relationship between 7 and 3 or 10. So instead of that, you use 3, okay? You use all threes. So 3 times 3, that is 9 times 3, that is 27. Do you understand? So in this case, you have, oh, sorry, 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 sorry. So in 27, you use 10. Sorry, I was thinking from really what direction. So in 27, what we do is that we take it up to 30. We take it up to 30, but then we remove 3 from 30. That is 27. Does that make sense? So 30 minus 3 will give you 27. So 30 is 3 tenths. So 10 plus 10 plus 10. So on the other side, it becomes uh, let's do the tax. Let me use uh, hold on. I'm going to use spreadsheets to show you what I'm calculating. So that's it makes sense. You're doing 27. Okay, so you're doing 27. Okay, can you see my screen? Awesome. So you have the DB here, 27. 27 calculation. Okay, so 27 is equals 30 minus 3. You understand? Do you get it? It's awesome. So instead of that, we would now say, we have 30. 30 is 10 times 10 times 10 uh, times 10. That is 30. Okay. Oh, what am I saying again? Yeah, it's plus, not times. Okay. That's the 30. And then we have a 3. Okay. So 3, so 27 is 30 minus 3. That's 27. This is what we want to achieve. So in the milliwatt side, we want to achieve this. Remember, whatever you add in decibel, you multiply in milliwatts. So that is 10 times 10 times 10. That's 1,000. Okay, milliwatts. But 3 here, you're adding 3, or you're subtracting 3 to get it to 27, right? So 3 is what? Is 2, right? So this time around here, you see, you have a minus. In milliwatt side is division. So you have 1,000 divided by 2. Make sense? Does it make sense? Oh, okay, that's okay. Let's do it again. Oh, good, 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 good. I need like immediate response. I thought you didn't get it. Okay, you got it right. So let's play with a few more. Can we? Not this one. Yeah. Can we? Can can we do 15? No, feel free. Tell me. So what is 15? What is 45? What is 1 dB? Let's do 15 first. What's 15? In milliwatts? 15 dB? In milliwatts? What did that be? Do it together. Can say? Tell me. What is 15 in dB? 15 in milliwatts? 15? 15 will be what? What's the property of 15? Tell me. Let me give you a
Three
cheat.
and 3 plus 3 plus 3 in 5 places.
Absolutely. You can do that. So 3 plus 3. Are you sure? Plus 3 plus 3 plus 3. Will it that give you 15? Yes.
Yes.
Okay. So you can say um 2 times 2 times 2 times 2 times 2 in 5 places. Right? Awesome. Let's try another way. 15. 15 is 10 plus 10, plus 5, right? How do you get 5? You can't. Okay. So who can do 45 for us? Please go ahead. Tell me.
I don't know how you get 32, sir.
Ah, my math is bad.
I don't know how you get 32.
Okay. Let's. What did you get?
I haven't calculated, but I don't understand how you got 32.
Sure. Let's do it again. Is anybody having the same doubts too? Okay. So let's do this way. Very easy. So you have 3 in 5 places. 3, 3, 3, 3, 3. Okay? And that is 15. Okay? 15 is what you're trying to do with. If you add it, this is what you get. So let me put it in this slide first. So start from here. It is initially 3. Okay? And then the next one, as time we go, it is another 3, the second 3 plus the first 3. And then this is the 3 plus this one above, right? And then this is 3 plus this, and then this is 3 plus this. That's 15, right? You are still with me, right? With that? So whatever you're adding in decimal side, you multiply in milliwatt sides. So you said it is 3, okay? 3 means 2, okay? So 2, and then the other one, the all 2, right? 2, 2. I talk about these threes. There's a 2, and this last 3 is also a 2. Okay. But in here, we had it to get our 15, right? Here, you're going to be multiplying to get our answers. So the first one is 2, okay? The next one is 2 times 2, that's 4. And then it is 2 times 4. And then it is 2 times 4, 8. And the last one is 2 times 16. So your 15 dB equals 32 milliwatts. Milliwatts. Is it clear? We can do it again. Okay. Let's look at this guy that we did earlier. Let's look at this guy. We did earlier. It's 27 dB. 27 dB is 30 minus 3. 30 is 10 plus 10 plus 10. That is 10 times 10 times 10. 3 is 2 dB. But to get 27, you remove 3 from 30. So remember the rule. Minus means divide. Plus means multiply in milliwatts. So because we subtracted 3 from 30, we are going to divide 1,000 by 2 to get 500. Does that make sense? Okay, let's do one more. Let's do one more. Let's do 45. Maybe that will be clear. Or let's review this first, okay? Oh, somebody's blazing. Okay, wait. Okay, let's do one more. Let's review this again for the benefit of Margaret. Okay, please. So we have 10 dB. Okay, in dB, 10 is 10. Okay, nothing changes. But what changes is that in dB, if you are multiplying, if you are adding, that is plus. In milliwatt, we multiply. So subtracting in dB, we divide. So if you have 10, it's 10. If you have 3 dB, it is 2 in milliwatts. So if you say 13 dB, that is 10 plus 3. That is 10 times 2. That is 20. Earlier, I did 36. 36 is 3 tens plus 2 threes. That is 30. Let's do that. 36. Okay, 36 means I have 3 tens. 10, 10, 10, and I have 2 threes. 3 and 3. So 10 is 10, okay? In milliwatts, 10 is 10, and 3 is 2, right? Since we are adding, the that is and I'm multiplying, okay? So I start with 10 times 10, and the next one equals 10 times 10, okay? And the next one equals 10 times 100, and the next one equals 2 times 1,000, and the next one equals 2 times 6,000, and give us 4 4,000 milliwatts, right? Is that clear, Margaret?
Yes, sir.
Are you good now, right? Okay. Are you sure? Okay. So yeah, go ahead.
I'm sure, sir.
Oh, okay, great, great, great. So I saw what you're doing for the five earlier. So for the five, you have 30, 10, and then you added. Hmm, interesting. Let's do it in a different way, okay? You want to achieve for the five, okay? For the five. So what do you add together? You want to keep it in tens and threes, okay? You are not doing anything outside tens and threes. Tens and threes. So I have 10 plus 10 plus 10, that's 30, plus 3, 33, plus 3, plus 3, plus 3, plus 3, plus 3, right? So if I add it together, let's see, you have one at a time. Let's really wrap it up. So that is um, about that's 5, okay? If you add it together. So this is in dB, that will be 10, all, this is 10, and this is all 2. Okay, now let's do the calculation. So you have a 10, and a 10 times 10, and another 10 times 100, and another 2 times 1,000, and another 2 times another 2,000, and another 2 times 4,000, and another 2 times 8,000, and finally there are 2 and 16,000, another 32,000 milliwatts. Is that clear? Okay, so pretty much that is the calculation. Awesome, awesome, awesome. So that's pretty much the calculation. Oh, please go ahead, shoot. Go for it.